All right. Cool. So, hello, everybody. Hello. Welcome back to CE 347, Urban Stormwater. I got an exciting lesson for you today. A couple announcements before we get started. First, homework 1 is graded, and the grades will be posted soon. Before I move on with the announcements, I want to have Becky give a quick announcement about, just the grading of the homeworks and what her expectations are for you. So Becky is doing the grading for the homeworks. So she's going to give you a quick rundown of just her expectations for future assignments. Okay, so just so that you're aware. Okay, Becky. Okay, so just to be clear, the three major. Oh, thank you, Becky, by the way. And Becky's been spending a ton of effort grading your homework and going the extra mile. So I just want to say thank you, Becky. So the three major things were, first, make sure all the pages are assigned. So what happens if you don't assign all the pages? Minus 25% on the problem for which you did not assign pages. Okay. The next thing, show your work. What happens if you don't show your work? You get a 0 credit on the problem. Okay. And the final thing, units. What happens if you don't carry through your units? Minus 10%. Okay. So just so we're clear, that will apply for all future homeworks going forward in the class. Okay. Yes.
For this next homework where it's like Excel or the graphs, are we putting in it or just putting how you want to show our work?
Show the spreadsheet, like take a screenshot of the spreadsheet if you use the spreadsheet. And for code, just post your code. Yeah. Yes.
Find my variables as we this summer, and then next we can just variables. Is that enough work? And maybe also show each number.
Could you repeat the first part of that? I'm having trouble hearing. Mm-hmm.
And then how is that enough work, or should I also like show me something?
Yeah, so I believe, and Becky can correct me on this, but the time you'll want to show your units is when you actually substitute in the numeric values for those variables. That's usually the convention. So yeah, if you just have it defined as h is equal to 2 meters, when you actually show substituting in the numeric values, that's when you put in the units. Is that right, Becky? Okay, cool. All right, cool. Any other questions? Yes.
So you want the units in the equation itself, not just the answer?
Yes, yes, and in every step of the equation. Yes. Okay, cool. Any other questions? Okay, cool. So homework 1 is graded. That's going to be posted soon. Homework 2 will be due next week. Make sure you are getting a head start on that. In particular, the Green-Ampt problem is a lot of work. So if you haven't started that already, please do not wait for the last minute to do that problem. And I'm going to be going through parts of it today to help you out a little bit. The final announcement, next week, we're going to be doing an in-class exercise with ArcGIS. So I will post an announcement with instructions for installing that, but I will need you to install that before we get to class on Tuesday and make sure everything is running, just so that we can proceed faster during the in-class tutorial. So I'll post instructions for how to install ArcGIS, how I want you to install it. And that will be next week. Okay. Are there any questions before I move on? Cool. All right. Okay, so let's do a quick recap. So last time we talked about the Green-Ampt model of infiltration. This is a kind of a classical model of infiltration that's used all over the place in stormwater engineering. So this is a model that's used within EPA stormwater management model. It's used in HEC-HMS. And it's probably the closest thing you can get to a physically based infiltration model in the stormwater domain. And the Green-Ampt model, I went through the derivation for Green-Ampt, and I also presented a conceptual overview of how the Green-Ampt model works. So essentially you have a soil volume, you have some rainfall falling over the soil volume. And you begin to create a sharp wetting front at the top of the soil that kind of moves downward over time. Okay, and so in the Green-Ampt model, it's assumed that everything above the wetting front is completely saturated, and everything below the wetting front has the initial soil moisture content, which we call theta naught. Okay, and as that wetting front moves down, the infiltration capacity of the soil decreases, and so you'll get a infiltration rate curve that looks something like this. Okay, so you start off with an initial infiltration rate. By the way, let's call the rainfall rate WT. So we start off with an initial infiltration rate that is equal to WT. And then the infiltration capacity of the soil decreases as the wetting front decreases. And the corresponding actual infiltration will also decrease as that potential infiltration decreases, okay? And I gave you the equations for the Green-Ampt model. We derived these in class, essentially from Darcy's law, okay? Capital F of T, this is, what was this called? Does anyone remember what this was called? Yeah, this is the cumulative infiltration. I'll call it the cumulative infiltration depth because it's in units of length. What is this here? This is the infiltration rate. This here, what is this? The ZF of T? This is the literal depth of the wetting front. And TP, we didn't really talk much about this, but this is the time to ponding. So you'll need this for the homework. And what this is it's the time at which ponding starts to occur at the soil surface. So it would be this point right here on our curve. So after we reach the time to ponding, the infiltration capacity of the soil is less than the rainfall rate, and you'll start to get water pooling on the surface. Okay. And once you get water pooling on the surface, you will start to experience runoff, and our runoff rate, which we call RT, is equal to the rainfall rate minus the infiltration rate. And I can't draw any further on the screen. Let me just put it down here. Okay, great. Are there any questions conceptually on Green-Ampt before I move on? Any questions conceptually on Green-Ampt? Okay. So at the very end of class, I posed this question to you. Why is it that the infiltration rate F of T decreases over time? We know that in the Green-Ampt model, we have that the wetting front is created at the instant that the water falls on the land surface, and that everything above the wetting front is completely saturated. So why is it that FT, the infiltration rate, gradually decreases over time? And I kind of hinted at this last time, but in your own words, can anyone explain why the infiltration rate decreases over time? And I have a hint here up on the slide. Anyone want to venture kind of an explanation for why the infiltration rate decreases gradually over time? And these equations up here may give you a hint. Yes.
Just off intuition of the equations, that the available space for water to be collected fills, and so then there's less space to be filled as the rainfall continues.
That's true. But in our Green-Ampt model, remember, we assume that everything above the wetting front is completely saturated, meaning that that entire volume is filled with water, right?
Does the wetting front rise?
So the wetting front goes down over time. The wetting front moves down. And anyone want to venture kind of a explanation in terms of these equations why the infiltration rate decreases? Oh, yes.
As that
Mhm. Yeah, so F of T will converge over time to the saturated hydraulic conductivity, right? And that's what we showed at the very end of class last time. As Z F of T goes to infinity, F of T will approach the saturated hydraulic conductivity. More generally, though, what's happening to this term here as the depth of the wetting front increases? Does it start out greater than 1 or less than 1? Does this term here, dH by dz, start out greater than 1 or less than 1? Greater than 1, right? This term here starts off greater than 1 because we have the matrix potential, which is positive here, as denoted by these absolute value signs, plus ZF of T over ZF of T. Okay, so basically this hydraulic head gradient here is decreasing as the depth of the wetting front increases. Okay. So it starts off greater than 1, and then as the depth of the wetting front increases, it eventually converges to 1, meaning that the infiltration rate converges to the saturated hydraulic conductivity. Okay. Are there any questions on this concept before I move on? Yes. So this Green-Ampt model is kind of a simplification of the real world physics because we assumed that the wetting front is sharp and piston-like with everything above completely saturated and everything below unsaturated at the same soil moisture content. And so when we went to go compute our Green-Ampt model, we approximated this dH by dz as a single approximate value delta H over delta Z. So we're just looking at basically when we're looking at that gradient, it's just defined over the length of the wetting front. So in reality, you would have kind of gradations of volumetric soil moisture within the wetting front as it's coming down. In this case, though, it assumes everything above the wetting front is completely saturated. So this is basically approximating the way that the hydraulic head would decrease over time by representing it as kind of a single block that's moving down. But you can think in the general case, though, as the wetting front increases, the hydraulic head gradient will decrease in reality as well. It's just kind of a more complicated to model. Yes.
Can you explain why the wetting front goes down?
It's just because water is moving down due to the force of gravity, right? So as the water falls on the soil, you'll kind of get this layer of water that's traveling down just due to gravity's pull. Yes.
Actually, there's my question letter. What does that physically mean as the infiltration rate approaches the saturated height?
Well, it means that the infiltration rate will kind of converge to a value on this plot here. So, somewhere down the line, the infiltration rate that's allowed at the top of the soil is going to converge to the saturated hydraulic conductivity. So what this infiltration rate here is describing is the amount of water that the surface of the soil is admitting, the rate of inflow to the soil that it's admitting.
Okay, yeah. And then the saturated is just based off of the sediment, right?
Yeah, it's based on intrinsic properties of that soil that you're interested in. Yeah. Yes.
I guess visually I'm stuck on the swimming pool filling up instead of the water infiltrating down. So do we assume that there's like a false bottom? I forgot the term. We're not assuming that it's like filling up.
So, well, what would happen if you had like a bucket of gravel and you poured water into it?
It would eventually fill.
Right, but what if you had an infinitely long bucket of gravel?
Keep falling from-
Yeah, the water will just keep falling. So it's the same thing. In this case, though, as the soil particle size gets smaller, there's more forces essentially pushing the water back up, so it moves more slowly down that cylinder, right? If you're talking about a bucket of soil. So the wetting front, it just is describing, you know, the water that's progressing down. You know, if it was gravel, it would move through very quickly. So it would just be like dumping a bucket into another bucket and the water just falls. The only difference here is that the soil has forces that are pushing the water back up, so it moves more slowly.
No, just trying to understand, not be difficult here, but as I understand why the infiltration rate slows down, like that makes sense intuitively, but then I guess I'm thinking that like for the rate to slow down, like that level would have to rise. So I guess I'm trying to visually conceptualize the infiltration rate decreasing and the table decreasing.
Yeah, so that is what will happen. Yeah, the wetting front will decrease in its elevation, so the wetting front will move down, and then at the same time, the infiltration rate will decrease. I'm not sure how to give intuition for it, but you might try.
So it keeps going down. The wetting front goes down at a slower rate. Is that
Yeah,
okay?
yeah.
Thank you.
Okay, cool. Yes.
I don't know. But I'm thinking about it, like when you're watering a plant and it's like you haven't watered in a while, and so like when you finish your water, like all the water is at the top, and like that's fully saturated, and then it starts to like stuff.
Yeah, that could, yeah. So think about watering your plants at home and how the water behaves in your potted plant, because that's basically the same thing that's happening here. Yeah. Okay. Cool. Any other conceptual questions? Okay, who started on the Green-Ampt problem on the homework? Oh boy. Okay. So I'm telling you right now, it's a difficult problem and it's going to take a while to do. So do not wait for the last minute to start this problem. Okay. So I'm going to help you out. So I'm going to go through an example. First, I have to give you a quick detail that I skipped over. So in our equations, we have this expression for the matrix potential. I didn't give you a way of computing this. This can be looked up for different soil types in tables, but for the homework, you will be using an equation from the notes. So there are various empirical methods for computing matrix potential. We're going to be using this one. Okay, so our matrix potential, this is from the Brooks-Corey formula. Our matrix potential is equal to the following expression, and I'll just say the variable names and then I'll tell you what they are. 2b plus 3 over 2b plus 6 times psi AE. Okay, so as before, this is the matrix potential, and this is in units of length. It's in units of length. B is the pore size distribution index. Pore size distribution index. This is unitless. And this is essentially a measure of how heterogeneous the pore size distribution is in the soil. And this psi AE, this is the air entry pressure. And this is something that can be determined experimentally, which is why it's often used in formulations like this, but it essentially describes the minimum air pressure acting on the fluid that is needed to allow air to enter into the soil. So it's sometimes also called the bubbling pressure. It's not really that important what it is because it's mostly an experimental variable, one that's determined by experiment. But we'll be using this expression in the homework to compute the matrix potential. So just make sure you know this. There are other models for computing matrix potential, and often you can just look it up in a table. Okay, so I'm going to give you a quick example just to assist you with the first parts of the problem. Okay, so we're going to be looking at, let me give you an example. Okay, and what I want you to do is, for the following soil, determine if ponding occurs. And if so, compute the time to ponding. And I'm going to do this with you. Okay, so we have the following soil parameters. Let's say that our rainfall rate W is equal to 5 centimeters per hour. Our porosity is 0.5. Our initial soil moisture content is 0.1. Our saturated hydraulic conductivity is equal to 0.0004 centimeters per hour. Oh, sorry, centimeters per second. Units. Our air entry pressure is equal to 60 centimeters of head. And our pore size distribution index is 6, and this is unitless. So just to be explicit, unitless, unitless, unitless. Okay, and so we're going to determine if ponding occurs. And if so, we're going to compute the time to ponding using the formula I showed you earlier. Okay, was there a question on the, okay, a question? Nothing? Okay. Cool. So how do we compute whether or not ponding occurs? How do we compute whether or not ponding occurs? Any ideas? Yes.
If the infiltration rate is higher than the conductivity, then.
So close, it has to do with the saturated hydraulic conductivity. So what needs to be greater than the saturated hydraulic conductivity for ponding to possibly occur? The rainfall rate. Yeah, it's the rainfall rate. So we have to determine whether the rainfall rate is greater than or less than the saturated hydraulic conductivity. So, right, because if we go back to our plot, right, in this case, our rainfall rate is right here. And the saturated hydraulic conductivity is the infiltration rate to which the soil converges, right? So it's only possible for it to pond if the rainfall rate is greater than the saturated hydraulic conductivity. Okay. The rainfall rate is less than the saturated hydraulic conductivity, the water will just pass freely through the soil and there will be no ponding. Okay. Okay, so let's go ahead and compare the rainfall rate against the saturated hydraulic conductivity. We have to change units on the rainfall rate really quick. So let's say W is equal to 5 centimeters per hour. We can just multiply this by 1 hour. 1 hour over 3,600 seconds. And that gives us a rainfall rate of 0.00138 centimeters per second. Okay, and remember our KH star was equal to 0.0004 centimeters per second. So will ponding occur or will ponding not occur? Ponding will occur. Okay, so we have that the rainfall rate is greater than KH star, and thus ponding will occur. Okay, so this is the same procedure you're going to use on your homework. Okay, next, let's compute the time to ponding. We have from our expression, and this is basically just obtained by finding the line where the potential infiltration rate intersects the rainfall rate on our plot. The time to ponding is equal to KH star times the matrix potential times the initial soil moisture deficit divided by rainfall rate times quantity rainfall rate minus saturated hydraulic conductivity. Okay, so there's a couple of variables we need to compute here. First, what is delta theta? What is that equal to? What is delta theta? It is our initial soil moisture deficit. So how is that expressed mathematically? What is delta theta? Sorry? Yeah, so it's the porosity minus the initial soil moisture content. So this is essentially the amount of space that is left to fill in your initial soil volume, okay? Okay, and we can compute this. This is equal to 0.5 minus 0.1, which is equal to 0.4. Note that there's no units on this. Okay, and the final thing we have to do is we have to compute the matrix potential. So from our expression before, we have psi f is equal to 2b plus 3 over 2b plus 6 times the air entry pressure. Okay, our b is 6, so the numerator ends up being 15. Denominator ends up being 18. And our air entry pressure is 60 centimeters of head. Okay, and so what we end up with is a matrix potential of 50 centimeters. Okay, so all we have to do now is go back in and plug in those values. So I'm going to go ahead and do that. Okay, so for our saturated hydraulic conductivity, we have 0.004 centimeters per second times matrix potential is 50 centimeters times initial soil moisture deficit of 0.4 divided by a rainfall rate of 0.00138 centimeters per second times quantity 0.00138 centimeters per second minus 0.004. Sorry, one more zero on there. 0.0004 centimeters per second. Okay, and that will give us a final value of 5,915 seconds. Okay. Great. So that is essentially the same procedure you will need to follow on your homework. I wanted to walk you through it just to prevent you from getting tripped up because the later parts of the problem are somewhat difficult. Okay. Are there any questions in how this was computed? Any questions? Okay. And a quick quiz. What is the infiltration rate before ponding starts to occur? What is the infiltration rate before ponding starts to occur? As a number. Yeah, which is 5 centimeters per hour. Good. Okay. So please remember that when you do your homework, before ponding occurs, the infiltration rate is equal to the precipitation rate. Okay. So when you're plotting the infiltration rate, make sure you include that part, okay? That's a common error I saw last time I assigned a problem like this, okay? Okay, are there any questions before I move on? Cool. Okay, well, that's it for Green-Ampt. Again, this is a super important infiltration model. It's probably one of the most commonly used infiltration models, one of the most common ones you'll see as a practicing stormwater engineer. So make sure you kind of understand the fundamentals and know how to use it. Okay, great. So the Green-Ampt model is essentially the fanciest model you're really going to use in practice in stormwater engineering. It's the closest we'll get to a physically based infiltration model, but oftentimes, having a fully physically based or, partially physically based model of infiltration isn't needed all of the time. So what I'm going to show you next is a method that's widely used in practice that is a bit easier to compute than the Green-Ampt model and often works very well in practice. And that method is called the Soil Conservation Service method. Oh, it's hard to talk and write at the same time. Okay, Soil Conservation Service, or SCS method for computing infiltration. Okay. So this is a simplified empirical model that is nonetheless extremely commonly used and also extremely important for you to know. It's used widely in HEC-HMS, it's used in SWIM, just like Green-Ampt, but it's essentially an empirical model, whereas the Green-Ampt is physically derived. And even though it's relatively simple, it's still used for a number of reasons. So the first reason is that, well, as I mentioned, it's easier to compute than Green-Ampt. Okay, on a related note, reason number two, often the data that we need to use the Green-Ampt model is difficult to obtain. So data needed for Green-Ampt is difficult to obtain. Okay, so remember, to use Green-Ampt, we need estimates for the saturated hydraulic conductivity, and we also need estimates for the matrix potential. Okay, and in order to determine those parameters, you have to often go out and measure them in practice because soil varies so much from one location to another. It's hard to know what the exact values of those parameters are. And thus, to get calibrated models for Green-Ampt, it's often very labor intensive. So data needed for Green-Ampt is difficult to obtain. The SCS method, instead of using those physically based parameters, often uses empirical parameters that are tabulated for different land cover types that are much easier to use. And the third reason is that it is, the SCS method is written into many drainage codes. Okay, so it's written into many existing drainage codes, okay, such that the design of your stormwater infrastructure is often regulated to, regulated to be amenable to an SCS method for computing infiltration. So often, as you'll see later on in class, the Austin Drainage Criteria Manual specifies, different infiltration types to use for the city of Austin. It specifies different SCS parameters that you're expected to build your drainage infrastructure to meet. Okay, so it's something that's often explicitly written into stormwater regulations. Okay, and conceptually, you can think of the SCS method as kind of being an empirical approximation of the Green-Ampt method. It treats a stormwater basin as a set of hydrologic units that are classified by their land cover, by their soil type, and by their antecedent wetness or initial moisture content. Okay, so let me just write that down. Okay, SCS treats basins as a set of hydrologic units classified by land cover, soil type, and antecedent wetness or antecedent wetness. Okay, so let me give you a conceptual overview of the SCS method before we get into how to compute the SCS infiltration and runoff. Okay, so in a sense, it behaves much like Green-Ampt does. So let me give you a conceptual overview of what's going to happen here. So let's say we have the following plot. Okay, and let's say we have some rainfall. So the y-axis, this is going to be our precipitation rate. I'll just write precip rate. Okay, so this might be in, for instance, inches per hour. And this axis here is time. Let's just say it's in hours or something. And we'll have a rainfall event falling over a catchment of interest. Okay, and that rainfall event might look something like this. We're just going to kind of conceptualize it as a series of blocks here. Okay. So this is our rainfall rate over time. And we can divide this rainfall rate into a couple of different portions. Okay, so the first portion is going to be this portion right here. And this is our initial abstractions. Okay, so let me write these out. So we can divide our rainfall hydrograph up into a couple of portions. The first is our initial abstractions, which will denote IA. Okay, and this consists of a couple different things. Does anyone remember what some of the things I mentioned for initial abstractions earlier on in the class? Yes?
Vegetation?
Yeah, so like interception by vegetation. So I'll just write out the different types of initial abstractions that can occur. So we have plant interception. We have depression storage. So water that gets trapped in local depressions in the landscape. And initial abstractions also includes things like evaporation in this context. And probably most significantly, it also includes, for the SCS method, the infiltration before runoff begins. So it also includes infiltration before runoff begins. So we have some, so in our rainfall event, we have some initial component of the rainfall that is lost to initial abstractions. And then for the remainder of the rainfall events, we have, much like the Green-Ampt method, we have essentially a division of the rainfall into two parts. The first part is the infiltration, which I'll call FA. And in the Green-Ampt, in the SCS method, this is called the retention abstractions. So you can think of it as just being the infiltration after runoff begins. Okay, so this is FA. And this I will define as infiltration after runoff begins. Okay, and it will generally decrease with time. The other component is, what do you think the other component is? This part above the line here. Runoff, right. So what they call it in the SCS method is PE for the excess precipitation. Okay, so this is the excess precipitation, or PE. And this is essentially runoff. Note that they call it excess precipitation because runoff generally refers to, water that isn't infiltrated, but is also flowing in some way. The SCS method is just computing the volume of rainfall that doesn't infiltrate, essentially. So that's what PE is. That's what the excess precipitation is. It's the volume of water that does not infiltrate. Okay, cool. So conceptually, this looks rather similar to the Green-Ampt model. We have, some initial time at which all of the water is either being captured by depression storage, plant matter, whatever, or just infiltrating into the soil. Then after some amount of time, we start to get a division of the rainfall into excess precipitation and infiltration. Okay, so the SCS method makes a couple of assumptions, which I will kind of enumerate here. Okay, so we're going to make a couple of assumptions. Okay. So assumption number one, we're going to assume that the total rainfall P is equal to the sum of those three components. Okay, so the total rainfall P is equal to the excess precipitation plus the initial abstractions plus the retention abstractions or infiltration. Okay. So that's, not a bad assumption. Note here that P, this is the total cumulative precipitation. So this is not the rate, this is rather the total amount of precipitation that has fallen by that point in the storm event. Okay, so you could think of it as being the area of this entire plot here. Okay, so that's our first assumption. Okay, the second assumption is that there exists some maximum possible retention, which we will call S. So there exists some maximum possible retention, which we will call S. So you can think of this as the total storage available in the soil. Okay. So there exists some maximum possible retention S, and FA is less than or equal to this maximum possible retention. Okay. And FA is less than or equal to S. Okay. And the third assumption, probably the least realistic assumption, but the one that allows us to compute the excess precipitation, is that the ratio between the actual infiltration and the maximum infiltration is equal to the ratio of the excess precipitation to the total amount of rainfall that has fallen. Okay, so I'll write that out mathematically. The SCS method assumes that FA over S, in other words, the ratio of the actual infiltration to the maximum possible infiltration, is equal to the excess precipitation divided by the total precipitation minus the initial abstractions. Okay. So this is a big old assumption. Let me just label these. So this is this component here This is the ratio of actual to potential infiltration. And this here is the ratio of runoff to total precipitation, not counting the initial abstraction. Okay, so this is basically just an assumption. There's no clear physical meaning behind this assumption, but it is the assumption that the SCS method uses. Okay. Are there any questions before I move on? Any questions? Okay, cool. So combining this equation here from 1 and this equation from 3, we can formulate a equation for the excess precipitation. Okay, so we're going to combine 1 and 3 together. Okay, so if we take a look at equation 3, we note that from equation 1 that FA is equal to P minus PE minus IA. Okay, so we can substitute that into 3. We have that P minus IA, the initial abstractions, minus the excess precipitation, divided by the maximum possible storage is equal to the excess precipitation divided by the total precipitation minus the initial abstractions. Okay, so I'm going to multiply through both sides by this denominator here. We end up with P minus IA times P minus IA minus PE is equal to PE times S. Okay. And if we expand out this product here, we get P minus IA squared minus P minus IA times the excess precipitation is equal to excess precipitation times maximum storage. And then we can rearrange for PE. We get that PE times quantity P minus IA plus S is equal to P minus IA squared. And then all we need to do is rearrange for PE on the left-hand side, and we get that the excess precipitation is equal to total precipitation minus initial abstraction squared divided by total precipitation minus initial abstractions plus the maximum possible retention storage. Okay, so this is the fundamental SCS equation. Now, in practice, actually computing the initial abstractions is really difficult to do. So the SCS method provides guidelines for computing those initial abstractions. So from SCS guidelines, it's generally assumed that the initial abstractions are equal to about 20% of the total maximum storage. And this is based on a bunch of empirical studies of real world existing small watersheds. It's generally assumed the initial abstractions are equal to about 20% of the total storage. Now, this is kind of based on older data. In recent years, it's been found that the initial abstractions are more like 5% of the total storage. But many existing drainage codes still use this version of the initial abstractions. Okay, so what I'm going to do is I am going to finish deriving the SCS equation. I am going to then show how you can use this to compute the excess precipitation or runoff for an example catchment with given land cover data. Okay. Okay, so if we substitute this value back into our expression for the excess precipitation, we get that the total excess precipitation is equal to quantity total precipitation minus 0.2 times the maximum storage, all squared, divided by total precipitation plus 0.8 times the maximum possible storage S. Okay, so this is the equation you will usually see. This is how it's presented in HMS and SWIM. Okay, and just to be clear, this is basically the total runoff. This is the cumulative runoff. Cumulative runoff. This here is the cumulative precipitation. So it's the total depth of precipitation. So for instance, if you have a rainfall that drops 1 inch of water, your P will be 1 inch. Okay. Yes. Yes. So they're both, this is, this is dimensionally consistent. So this, they'll both be in units of length. Yes. Okay. So the last remaining parameter that we need is this value for S here. So this is the total storage. You can think of this as the total infiltration capacity available. And this is where what's called a curve number comes in. So SCS method is also sometimes called the curve number method. Okay, and what we can do is we can compute S using what's called a curve number. S, our total maximum storage, will be equal to 1,000 divided by Cn, which is our curve number, minus 10. Okay, this is an empirical equation. And the curve number depends on the land cover and the soil type for a given catchment. Okay, so the maximum value for the curve number is 100, and that would be for a completely impervious land cover. So what happens if the curve number is 100? Yeah, the storage will be 0. What happens to the cumulative runoff? What will that become? It'll be equal to P, right? Because this term becomes 0, this term becomes 0, you get P squared over P, which will be equal to P. Okay, so if the land cover is completely impervious, the curve number is 100. If it is completely pervious, it goes all the way down to 0. Okay, but most real world land covers will be in the range of about 70 to 95, 98, depending on how impervious it is. Okay, even something that you think of as being completely impervious, like a roadway, that'll have some permeability to it. So, well, it'll usually never go above 98 or so. Okay, so let me just show you a couple examples of curve numbers. So they are tabulated based on various soil and land cover types. So here's an example of some curve numbers for different land cover types. We have different agricultural land cover types here. And you can see they're generally in the range of about 70 to 90 something. The soil group basically depends on what kind of soil is underneath the ground. So A will be soil that drains really well, like sand or gravel. D will be soil that drains really poorly, like clay. And B and C will be somewhere in between. Okay, so the soil type will also change what your curve number is. And I also have an example here. Here's the Austin Drainage Criteria Manual's curve numbers. So they have essentially regulated curve numbers for Austin. And you can see various curve numbers for different soil types and land cover types. Okay, so for instance, if you have open space, lawns, parks, golf courses, and a well-draining soil, you might have curve numbers in the range of 39 to 68. Okay, if you have completely impervious surfaces like paved parking lots, etc., it's roughly 98, so very close to 100. Okay, so this is really nice because it gives us nice tabulated values for the infiltration capacity of a given land area, whereas with the Green-Ampt method, you would need to experimentally determine the hydraulic conductivity and the matrix potential. Okay, so SCS method makes it really, really simple to create models, essentially. Okay, so as I mentioned before, the curve number CN depends on three things. It depends on one, land cover type. Two, it depends on soil type. And three, which I'll get to a little bit later, it depends on the antecedent soil moisture condition. Which we will call AMC. Okay. One quick note I want to make, because we're going to use it for our example. If we have a land area with multiple land cover types, we essentially take a weighted average of their curve numbers. Okay, so for an area with multiple land uses, take the weighted average curve number. Okay. So let's go through an example of how to do that. This is going to be similar to a homework problem that you will have later on. Okay, so I'm going to give you an example. I'm going to go through it. I'm going to give you a little more information, and then I'm going to give you your own example to work on that's a little bit more complicated. Okay, so let's go through an example. Okay, so we are going to do two things. First, we are going to compute the curve number for a watershed with multiple land uses. I will give you those parameters in a table shortly. So we're going to compute the curve number for a watershed with multiple land uses. Okay, and then we, I'll just say, then compute the runoff response. I'll just say the excess precipitation. For 1 inch of rainfall. Okay. Okay, so we have the following table of land uses I'll give you. Okay, so we're going to go land use. We're going to go, what's the percent of the area that's taken up by that land? What is the soil group? And what is the ultimate curve number? So normally you would determine the curve number based on the soil group and land use by looking it up in a table, but in the interest of time, I will just give you the curve numbers here for each of these. Okay, so we have residential. This is about 40% of our catchment. Soil group C, and our curve number for that land use is going to be 83. Okay, we have 25% open space in good condition. So this is going to be about 25% of our watershed. Soil group D, and its curve number will be 80. The third is commercial space. Okay, this will be about 20% of our watershed. Our soil group for this area is C, and the curve number will be 94 for this commercial space, presumably because it's more impervious than the residential space. And finally, we have 15% industrial. This is going to be 15% of our land area. soil group D, and curve number of 93. So I'll just give you a second to write all those down. So, as I mentioned, one of the nice things about this technique is you can just look up the curve numbers for various land cover types. Land cover data is easily available through GIS data. And so there's often a very convenient technique for computing runoff. Okay. So as I mentioned, the composite curve number for this entire watershed can be computed as the weighted average. Okay, so if we want the composite curve number for this entire watershed, we say that we take 0.4 for 40%, multiplied by curve number 83. So this is for our residential. Okay, we take this, we add 0.25% open space, which has a curve number of 80. Okay, we add a little bit of commercial, 0.2 times our curve number of 94. And finally, we add 15% industrial, which has a curve number of 93. Okay, so our ultimate composite curve number for this catchment is 85 point, actually, I'll just, okay, I'll write out the computations just so we can check it. Yeah, 33.2 plus 20 plus 18.8 plus 13.95, which adds up to about 85.95, which we will round up to 86. Okay, so conventionally, these are written as integer values. Okay, so that's how we can compute the composite curve number for a watershed with multiple land uses. You will need to do this in your homework. So I want to give you a quick example of how to do it here. Okay, are there any questions on that procedure? No? Okay, so how can we go about computing the excess precipitation associated with 1 inch of, oh yes. You can just round to the nearest number. Yeah, it's not really necessary because yeah, there's so much uncertainty involved here that, yeah, it's okay. Just by convention, you round it to an integer. Okay, so how can we go about computing the excess precipitation for this watershed? What's the first thing we got to do? Did someone say something about the storage? Yes, we got to compute the storage. So how do we do that? Yeah, so our storage is equal to 1,000 divided by the curve number minus 10. Okay, so if we plug in our values, we have 1,000 divided by 86 minus 10. And this is in inches, yes. And this will give us a value of 1.63 inches. Okay, so that's our total storage available per unit area for this catchment. What's the next thing we do? Okay, we use the equation for the excess precipitation. And so we have that the excess precipitation is equal to total precipitation minus 0.2 times S squared divided by P plus 0.8 times S. Okay, and let's substitute in these values. What is P? What is P? 1 inch, okay. 1 inch minus 0.2 times 1.63 is our storage. Okay. All squared divided by, ooh, cannot draw a straight line. Okay. Divided by P, which is 1 inch again. plus 0.8 times 1.63 inches. And if we evaluate this expression, what we get is our total excess precipitation is about 0.2 inches. Okay, so we infiltrated quite a bit. About 80% of our total rainfall was infiltrated, about 20% escaped as runoff. Okay, so there's one last thing I want to leave you with, and I will give you an exercise on Thursday where you can apply this knowledge. But as I mentioned before, we have to adjust for the initial soil moisture in our soil. So let me just quickly emphasize this because you will also need it for the homework. So let's just say adjusting for initial soil moisture. So generally, when you're looking at those tables of different curve numbers, those are essentially specified for kind of an average initial soil moisture condition. And you have to adjust either upwards or downwards, depending on whether the initial soil moisture condition for your real world catchment is really dry or really wet. Okay, so I will write out the equations. We'll say that CN2, this is our curve number for average AMCs or antecedent moisture conditions. And then for dry and wet conditions, we have to adjust upwards or downwards. Okay, so for CN1, this is for low moisture. Okay. And to adjust to a low moisture curve number, we take our curve number for average AMC and we use the following expression, 4.2 times CN2 divided by 10 minus 0.058 times CN2. Okay, so it's just adjusting our average soil moisture curve number to the dry conditions. And this is basically empirical. I'm just showing it to you here because you will need it for the homework, which is due next week. Similarly, for high moisture conditions. Okay, so this is high moisture. You might see this after a heavy rainfall event. Okay, to convert to a high moisture curve number, use the following equation, 23 times our standard curve number, which I'll call CN2, divided by 10 plus 0.13 times CN2. Okay. And let me just go back and make sure I didn't make a typo. Yeah, okay, we're good. Okay, so that is how you convert the curve number between medium, low, and high moisture. Yes, you have a question? We found CN2 for the last example, yeah. And for the Austin DCM, these are for a list, see how it says assuming ARC2 condition? They're usually specified in tables for the standard soil moisture condition, yeah. Okay, and that's all I have for you. Sorry, are there any last questions before I dismiss you? Any last questions on SCS method? Okay, cool. Well, yeah, have a nice rest of your week and I will see you later. Please come into office hours if you have any questions. And as I mentioned, get started on homework 2 early. Thank you.